In this video, we're going to take an in-depth look at advanced MapReduce. We're particularly going to explore shuffle and sort. We're going to explain what that is. We're going to look at partitioners, combiners, and comparators. And we're finally going to look at configuration to enable all of this. So before we get in too deep into shuffle and sort, let's actually look at how you think about it working logically. So if we start over here on the left with our input file, and we say that during the HDFS process, it distributed these lines so that each line appeared on one data node as one block of data. We've got our white data, our yellow data, and our green data. When our mappers spin up, they read this data in and they output locally on their local disk. They output the number of times that each word appeared in that line. So here you have this is line 1, and the number 1 appearing for each. So this is the key and this is the value. And similarly, the same thing happens for mappers 2 and 3. And then some sort of shuffle and sort magic happens, and on the reducer is presented with the keys in sorted order and the list of values all combined into one list, into a iterable list that we can go across in our reducer. So logically, this is how you want to think about things happening. But in reality, what really happens is something more similar to what we're going to walk through right here. Let's take a larger data set, and let's say that we have 3 regions that we operate across, US, Asia, and Europe. And let's say that these are sales figures for each region. So again, let's say that our blocks just so happen to break. Luckily, we have one set of 3 lines that appear on each slave. So here again, we have our white, our yellow, and our green data. And as the mappers spin up, they read these key value pairs. If we were using something like a combiner, they would actually output the name, the key, as the individual key in sorted order, and all of the values combined into one single list or number. In reality, if you didn't use a combiner, it would look a bit more similar to what we had on the previous slide. It's just that we would have the keys again in sorted order. So in reality, the map does half of the sort phase. So each mapper has sorted its keys individually, and because each mapper's data is a subset of the overall data, we see that not all the keys are represented. For example, mapper 1 is missing Europe, and mapper 3 is missing, looks like the US. What happens now is when the reducers spin up, they are going to reach out across the network, and they're going to ask each mapper to give them its individual keys. So the keys and all the values are pulled over, and then the reducer does another sort, and it sorts the keys again so that we have all the keys in sorted order, and it builds a list of all the values. So again, because we used a combiner on the mapper phase, and we'll talk about what a combiner is here shortly, we have our individual sales data for each mapper combined per mapper. So again, this data is presented to the reducer, and the reducer does one final sum of all the data. So we get Asia's total sales figure, Europe's, and the US. And this is what actually happens in the shuffle and sort phase. There's a map-sized sort, there is the shuffling of the bytes across the network, and then there is a reduce-side sort. So it's actually sort, shuffle, resort, and then the reducer runs. So the entire set of operations, the map and reduce side sorting, and the process of shuffling the data from the mapper to the reducer is together referred to as shuffle and sort. Logically, it's good to think of it as one separate thing that happens, but in reality, it's also good to know that half of it happens in the mapper and half in the reducer. We cannot turn off sorting in Hadoop, but we can control how things are sorted by providing our own custom comparators. Those that are familiar with Java are probably used to creating their own custom comparators. In Hadoop, this is especially useful for doing the secondary sort. So Hadoop, as we know, does key-based sorting by default, but with secondary sort, we can also put our values into sorted order. Again, if you remember, our values come in a random order in the list of values that's presented to the reducer. So where individual keys match, the list of values will then be used to determine the sort. This can be extremely useful for finding the maximum and minimum value amongst a list of values in a data set. We can create our own custom comparator function by either implementing a custom writable comparable or by using a comparator class. Those that are familiar with Java will be used to doing at least the comparator class. You do have to write these in Java, so even though we support streaming for the mappers and reducers in other languages, you have to write comparators and partitioners in Java themselves. The writable comparable needs to implement the equals, compare to, and hash code methods. And again, if you're a Java dev, you've probably dealt with these. And then to set up a custom comparator, we can call job.setSortComparator class and provide our comparator class in the driver. And again, we can also use our own custom writable comparable for the key type. And then the compare function on that writable comparable is what will control the sorting of our keys. We could, for example, with secondary sort, use a custom writable comparable by moving the value up into the key space so that the mappers would create composite keys such that we move the value, the $77 for the sale, up into the key space where we now have this entire key is US:77 and the value is only 77. More elegantly, we'd probably create a pair object in Java to take care of this. A combiner we can think of as a pre-reducer. The combiner, again, is completely optional, but if you provide one, Hadoop will use it. It will run on each mapper's final output, combining the results. So in the case of our sum reducer, for example, for our regional sales, the same class can be provided to our combiner, and we will do a pre-sum on each mapper's data. Again, this is often a sum reducer function, as shown on the earlier slide for the US, Asia, and Europe region example. And this can not only dramatically decrease the amount of space required for each mapper to output its intermediate data, it can also dramatically decrease the amount of data that we need to shuffle from the mappers to the reducers. And usually this can make our job run quite a bit faster by not only writing less data to the disk, but by transferring less data across the network. We simply can reuse our reducer code by calling the job set combiner class and specifying the exact same reducer class that we used for our reducer. When we use a custom partitioner, each individual mapper will output a partition file. For example, here, mapper 1 may output a partition file for Asia and a partition file for the US. If we had 3 individual reducers and each one were to handle an individual region's data, such that reducer 0 handles Asia, reducer 1 handles Europe, and reducer 2 were to handle the US. Then when each reducer reaches out to the mapper, it will grab the partitioned data from that mapper and pull over the partition that it is interested in. So for example, reducer 0 will only reach out to mapper 1 and pull over the Asia data, and reducer 3 will reach out to the same mapper and only pull over the US data. Additionally, the same reducer, reducer 0, will reach out to mapper 1 and pull its Asia data, each reducer only pulling over the data that it itself needs. So you can think of the partitioner as controlling which keys go to which reducer. The default partitioner, which is called a hash partitioner, simply runs a hash function on the keys and should, amongst a large enough key space, evenly divide the total number of keys amongst the total number of reducers. So for example, if you had 10,000 individual keys and 5 reducers, each individual reducer will get a random 2,000 keys. If you have 100 keys and 2 reducers, each one would get a random 50 keys. The hash partitioner, however, doesn't ensure that all of the reducer keys are less than the subsequent reducer keys. For example, if we had 6 keys generated across our entire data set and we only had 2 reducers, reducer 0 might get the random B, D, and E, and reducer 1 might get the random A, C, and F. Hadoop does, however, ship with something called a total order partitioner, and this can be used to ensure that all the keys going to a lower level or a lower numbered reducer are quote-unquote less than a higher numbered reducer, so that given the same keys, A through F, reducer 0 would get A, B, and C, and again in sorted order, and reducer 1 would get D, E, and F. We could then take the outputs of these 2 reducers and simply concatenate them together to get an overall sorted list of our output data. Custom partitioners can be very useful, and we can use these to ensure that each reducer is given a particular set of keys. For example, we may want our output data to be broken down by salesperson, by sales region, by month of year, time of day, so on and so forth. So given a key value pair, the custom partitioner simply needs to return a number of 0 through 1 less the number of available reducers. So if the job was called with, for example, 5 reducers, our custom partitioner would need to return a number between 0 and 4. We then specify this in our driver with a job.setPartitioner class, passing it the name of our partitioner. So some quick notes on using custom Java partitioners, comparators, and combiners. You obviously have to include the custom code in your jar file, in addition to specifying it in the driver call. And although our mappers and reducers can be written in any language, our partitioners, combiners, and our comparators and custom writable comparables have to be written in Java. Hadoop does ship with many of these pre-built, and we can go to these URLs right here to learn more about those. It's important to know that our overall flow of data is partition, sort, and combine. So an individual mapper will work on one key value pair at a time and output 0 or more lines to intermediate data. Once a mapper finishes all of its pairs, it then partitions out to an R number of reducers. So it actually creates an R number of partition files, which are still intermediate data written on that mapper's local disk. Each partition file is then sorted, the second part of our partition sort and combine, and any optional combiner code is run at this point. So for example, if we had a sum reducer, it would get run after the sort. The reducers still reach out to the mappers and pull their partition file that's specific for them. And then after all the mappers are finished and all the intermediate data is copied to the reducers can perform one final sort, and then the reducer function will work on individual key and lists of value pairs one by one. Remember that the V for the reducers is a list of all the values across all the mappers which found that key. After this lesson, it's probably very useful to go and review the partitioner code walkthrough video to actually look at some Java partitioner code in action. In this video, we've walked through advanced MapReduce. You should have a good handle of the shuffle and sort phase, and you should also understand at a pretty good level what a partitioner, a combiner, and a comparator is. We should also understand how to configure each of these and the limitations about them all being written in Java.